Welcome to this section on modeling. In this section, we shall work with the Csrnet model, which when given an input image and output density map can be used to train a people counting model. This model is based on the paper Dilated Convolutional Neural Networks for Understanding the Highly Congested Scenes by Yu Hong Li, Xiaofang Zhang, and Damin Cheng. In this paper, they proposed the Csrnet to provide a data-driven and deep learning method that can understand highly congested scenes and perform accurate count estimation as well as present high-quality density maps. The proposed Csrnet is composed of two major components: a convolutional neural network as the front end for 2D feature extraction, this what we generally call our base model, and a dilated CNN for the back end, which uses dilated kernels to deliver larger receptive fields and to replace pooling operations. Csrnet is easy to train because of its purely convolutional structure. The backbone of the Csrnet is a VGG16 model, and this was picked because of its flexible architecture for easily concatenating the back end for density map generation. We shall look at that shortly, and also because of its strong transfer learning ability. Looking at this configuration right here, we have four different possibilities. That's A, B, C, and D. We shall later on choose the B because of the results they obtained right here. This B had the least mean average error and mean square error. Anyway, we have this four possibilities, A, B, C, and D. Initially, all of them have the same kind of input. In this case, it's 768 by 1024. Then we have our base model, which is fine-tuned from the VGG16. Here we remove the top layers, so we're left with the first layers. Now, to see exactly the layers from the VGG16 which we shall use for the feature extraction, we have this here, this two 3x3 conv layers with 64 channels. We have a max pool. We have this two 3x3 conv layers, 128 channels, max pool. This one max pool 3x3, 512. And note that the dilation rate is equals 1 all throughout the VGG model. So basically, this is our base model, which is the VGG. Now coming to the back end, that's what they call the back end here. We have this. Let's take the case B. We have this 3x3 conv layer with 512 channels and dilation rate of 2. Also notice how it's very easy for us to leave from this output here and then continue with this back end layers. Now after going through this back end layers, we now finish up with this 1x1 conv layer with 1 channel and then dilation rate of 1. And then we notice that we leave from, or we have this input, and then the outputs need to be divided by 8 of this input. So we'll notice that after going through this first max pooling, we divide our input by 2. That's the input dimension is divided by 2. Then when we go to this next, we divide again by 2. So now we've divided by 4 with respect to the input, and then this we'll divide it by 8 with respect to the input. So this is how we ensure that we actually get an output which is 8 times smaller than the input right here. Now looking at the code, we are going to fine-tune our VGG16 model, which has been trained on ImageNet. We have the input, and in fact we have the input shape right here. We don't include the top. So let's run this. Here are the results we obtained for our VGG16 model. We see that it's a 14 million parameter model, which takes in this input and then goes right up to this, because we don't include the top. Now, since we are having an output which has this, we will notice that we shall actually use this first layers right up to this one right here as given in the paper, because in the paper we have this first 2 max pool, this 2 max pool, this 3 max pool, this 3. So we wouldn't consider this last or this layers before the last layer, because this isn't the last layers, because we've already decided not to include the top right here. Now what we'll do is we shall copy out this name. So we take this block 4 conf3, and then it shall be used now. So instead of having to output the model itself, we shall have this model output only at the level of this block 4 conf3 right here. So we have this block 4 conf3 which we pick out, and then we have it as our output. So that's it. We now return this model which has the inputs and then returns the output at this point, block 4 conf3 right here. Now let's rerun it again and see what we get. What we obtain now, we see we have this suitable output right here, which matches with what we had in the paper. Also recall that from the paper we are fine-tuning the VGG16 model, so we are not setting this layers to untrainable, so we don't freeze this first layers right here. Now we've had this base model, we could now go ahead to adding up the last layers, which in the paper they call the back end. We now define this layers where we have our input in X, in Y. We get the base model, that's what pass the inputs into our base model, which is what we've just defined. We have this random initialization, which is stated in the paper, and then the proposed to have the standard deviation of 0.01. Then following what's given in the paper, we have this 512 number of channels, 3x3 kernel, activation ReLU, dilation rate 2. We're following the part B, so that's why we have this dilation rates of 2, 2, 2, and then finally this of 1. And the pattern is same, so that we maintain this dimension of 96 by 128. Now we could run this, and there we go. This is what we have, so that's fine. Now we'll note that we also have to do this reshape, because after going through this conf layer, we have this 96 by 128 by 1, so we reshape this to obtain this value right here. Now once we have this, we are ready to train our model.